Hello everyone, welcome to another video in the lecture series of the theory of Raman effect. So before beginning this video, I'd like to give you a good news that I prepared a stand in my home for a camera stand, so for my phone, uh, due to which now my videos will be relatively more stable compared to the previous two. So yeah, let's begin. So just for a warm up, in the last two videos we saw uh, what the in the last two videos we saw what the polarization is. It's a vector which depends on the electric field and a tensor, and the elements of this tensor determines uh, what the polarization will be in any direction. So uh, and now we want to derive what uh, these tensor elements actually looks like mathematically. So before knowing that expression, we need to know some basic theories, and in the last video uh, I introduced you to time independent perturbation theory. And so in this video also we are going to meet with another new concept. So let's begin. So suppose you take a very simple system like uh, the hydrogen molecule. So, and the distance between the two hydrogens is given by r. So let the energy of this hydrogen molecule be E. Now you want to answer one question, is that how will the energy change if I change the radius of this hydrogen atom, like if I compress it or expand it, how the energy will change on changing the radius, so not the radius, the distance between these two atoms. So to answer questions like this, we are going to study today the Hellmann-Feynman theorem, which provides a very nice and simple answer for this. So like this question, we need to answer what the energy how the energy changes with respect to some parameter on which our Hamiltonian depends. So we need to find this. So before that, I let me tell you that in this video also I'm going to use the Dirac bracket notation, in which any inner product is just this integral, all space. So the energy, as we know, is just the expectation value of our Hamiltonian. So now suppose this hydrogen molecule is in one of the eigenstates, yeah, like it's in the ground state. So the ground state wave function is an eigenfunction of this Hamiltonian. So uh, so this will give the energy, ground state energy. So if it's in any higher excited states, is going to give the higher energies. So we want to study the change in energy with respect to any parameter. So this is just going to be the normal differentiation. This will give psi dh dp plus into psi, and so as you see, this is just the normal product rule for differentiation. So, and as I told that it's in one of the eigenstates, the hydrogen molecule is one of the eigenstates of the Hamiltonian. So if Hamiltonian acts on psi, it's going to give the energy of that state. So it's just E d psi dp psi plus, this is nothing but the expectation value of our Hamiltonian, and this in that in state psi, and this is and since the H is Hermitian, this is going to uh, this can act on the bra vector also. So it's again going to give us the energy. so it's just psi d psi dp. So now if you compare these two terms, combine them, you will see that it's just the normal differentiation of this inner product, and here we have again the expectation value of the change in Hamiltonian with respect to this parameter. So now this is just a constant. It's so differentiation of any constant will be 0, so this term goes to 0. This is just the magnitude of this that eigenvector, so differentiation of a constant will be 0, and so the resultant we now have dE dp equal to dH dp. So this is our Hellmann Feynman theorem. The spelling might be bhool, might be wrong. So yeah, so so now let's go back to our question. We had an hydrogen molecule, and now we want to know how the energy varies with this variation in our radius, not the distance between these hydrogen atoms. So our Hamiltonian looked like the kinetic energy of the nuclei plus kinetic energy of the electrons plus potential energy due to electron repulsion, electron nuclear attraction, and nuclear repulsion. So the only thing only expression in this Hamiltonian which depends on the difference between the two nuclei, distance between the two nuclei, is this term. This is just 1 by 4 pi epsilon naught r h1 minus r h2, or we can also write it as constant by r, and this whole Hamiltonian, just name it whatever, H non-nuclear. So our change in energy will now be dEdP equal to dDp of H non-nuclear plus constant by R, expectation value of this, and since this doesn't depend on R, this differentiation goes to 0. So we are, this parameter here is the distance between the two hydrogen atoms, so this is just k times minus 1 by r square. So you see, this is how the variation in energy if we change the radius looks like for this hydrogen molecule. So now this can help us interpreting many different things, but this may look simple, but we need to evaluate a general, or we need to construct a general expression for the eigenstates of the hydrogen molecule so that we can evaluate this expectation value. So not just R, we can also vary many different quantities, like we can introduce a static electric field in this hydrogen molecule, and let this be, then this let us vary it like electric field maybe increases, then decreases, then again increases. So we are so if we vary the electric field, and then if we want to know how the energy changes with respect to the changes in the electric field, we can again apply this Hellmann-Feynman theorem to look at how the energy expression changes. So yeah, that's what it's all about. If you have any doubts, please comment down below, and if you want the links to the last two videos will be provided in the description. And thank you, see you in the next video.